Hello, I am Shubham Sunil Dupar and I am presenting vehicle dynamics modeling and validation using Simulink and Assetto Corsa.
Model represents the vehicle longitudinal modeling. It converts the brake input into the braking force, longitudinal acceleration, and vehicle speed. The subsystem uses the Newton's law.
The car is Tatus FS01. The track is Silverstone. Here we can visualize the car. The car is speed till 180 km per hour. Later, before turn 1, the car has been stopped.
Now let's run the simulation. This graph represents the constant braking force during braking, and this graph shows the distance increasing while the vehicle slows down. Let's compare the Simulink model and the game model. Here we can see the Simulink XY plane shows the ideal straight line braking with zero lateral acceleration, while the Motec GG plot shows the real-world combined braking and cornering behavior with scattered loads. The model represents the vehicle lateral and aerodynamics. The purpose of this model is to convert the steering input to the lateral velocity and the yaw rate by using basic vehicle dynamic physics.
Here, steering input generates lateral forces and yaw moment, producing yaw rate and lateral acceleration, demonstrating lateral yaw dynamics.
The subsystem is the force and the moment calculation. The steering angle generates a lateral force tire by using a cornering stiffness and the geometry ratio to the sum block of new net yaw moment to get a total lateral forces and the total yaw moment. To the another system, by using Newton's law, we divide the total lateral force to the vehicle mass to get lateral acceleration. Same goes to the total yaw moment. It gets divided by yaw inertia to get yaw rate. They both get integrated over a time. Let's run the simulation. By visiting handling response graph, we can see the blue line indicates the reference or steady state response, while the yellow line indicates the actual vehicle handling response over time. This block is the your lateral dynamic model. The purpose of the model is to simulate and evaluate how the steering angle is predicting the slip angle, lateral forces, and the yaw motion, and overall handling stability of vehicle dynamics.
At this tight corner, the difference between vehicle motion and wheel direction produce front and rear slip angles.
This model calculates the front and rear braking forces using vehicle dynamics and combines them to evaluate braking stability. This subsystem calculates the slip angle calculation. This model compares the calculated slip angle with reference limit. Now we will see the graph. The left plot shows the smooth and ideal oscillatory vehicle path from the model, while the right shows the noisy but stable real and detailed response, highlighting the difference between the ideal simulation and the practical behavior. The front slip and the rear slip are calculated using the vehicle speed, yaw rate, and steering input. These slip angles are converted into tire forces using the tire force model.
Slip angles generate lateral forces at the front and rear tires, limited by tire saturation, which defines cornering and stability.
Now here we can compare the rear force analysis of this ideal simulation and the game data of the rear force analysis. This block represents the vehicle power strain and longitudinal dynamics. Its main purpose is to simulate how throttle input is converted into tractive force and vehicle acceleration, for allowing analysis of longitudinal performance such as speed buildup and the distance travel.
Throttle input generates tractive force through the power strain, increasing vehicle acceleration, speed RPM, and gear changes.
This dashboard represents the velocity, RPM, and gear. The plot shows the gear shifts, RPM drop, and the smooth speed increases. Here we can see the real and the ideal gap comparison. The blue one indicates the model and the yellow line indicates the real time speed of a car.
Thanks for watching my video.